So let's finally begin. Okay. All right. So that's the class of today. It's me, the third class. Okay. Optimal design. So today we enter a bit more into the problem of design. The problem in design the problem of assigning parameters of a task set which may be design variable. So why that? As I think in the first class, we mostly saw schedulability tests, and schedulability tests as have the problem of being just yes/no tests. So you have some given parameters, and you give them to the test, and the test tells you yes or no, depending on whether the task set is schedulable or not. Then the last class, we saw the sensitivity analysis. Sensitivity analysis is a bit more informative in the sense that it not only provides a yes/no answer, but it also provides like the margin that you can increase or decrease any task parameters so that you reach schedulability, that you can so you can reach the boundary of schedulability. Now, this more general problem, the problem of the design, it can be formulated as follows. So what if some parameters are left unspecified, meaning that you can choose the values that you want. And that's very common in control system design when you have to choose, let's say, the sampling period of the controller, or is it the question, or is it just an arm? Be careful with the arms. So it's right. So, or maybe if computation times are variables, meaning that you may be free to choose like the implementation or the accuracy of your task, which may affect the computation time. And this I call optimal design of real-time system. So how do we formulate in very broad terms? So we are given a set of n tasks, and there is a set of parameters which are design variables. So a set X of parameters, which may be periods, computation time, some parameters of the task set. And so then we also, now the ingredient is also a performance function that I call J, okay, from the set of design variables, X, to the real values. And these design parameters, this performance function returns how good are those design variables, okay? Right. So, the idea of this optimal design problem is to solve a problem like this, where we want to maximize the performance of the design variables, what we can play with, such that, well, of course, the variables belong to the set of the design variables, and such that the task set with these design variables aside is schedulable by fixed priorities. Now I'm considering fixed priority, but of course you can consider the very same problem with any scheduling policy or any. Sure.
So X is the X parameter, or is it the Y? Or is it
big X is the set of parameters, and the small x is the tuple of parameters.
Okay. Okay.
So let's say this is X, and this is X. Okay? Right. So, of course, if we want to be able to solve this problem, we need to understand the geometry of the feasible region. Because, for any optimization methods that you want to apply, then you need to know, what is the shape, what are the characteristics of the feasible values of X. Okay. So basically, what's the shape of this constraint of being schedulable? Okay. I like to introduce this notion because it's a notion that was introduced in the literature, and I think it's a notion that is also useful in this context of design. And it is the notion of sustainable schedulability test. Okay. So basically, well, this is just the notion as it is reported in the paper, As usual, I mean, that reference will appear in the notes. Okay, it's a paper by Barua and Alan Barnes. And well, the notion of sustainable is very simple, if you want. It means that well, let's see. A scalability test for a scheduling policy is sustainable if any system deemed schedulable by the scalability test remains schedulable when the parameters of one or more individual jobs are changed in any, some, or all of the following ways: decreased execution times, later arrival times, smaller jitter, and larger relative deadlines. What does it mean? In terms of feasibility, schedulability region, it means that, let's say that we have the schedulability region of computational time, C1 and C2. This condition means that if we have a point here, which is schedulable, then since now, I mean, they also prove that fixed priority and EDF are sustainable, okay? So since fixed priority and EDF are sustainable, if this point is either fixed priority or EDF schedulable, then also by decreasing computation time by any amount, meaning that moving in this direction, in any of this direction, by decreasing any of the component, we still are schedulable. Okay? That's the definition of sustainability applied to region of schedulable task parameters. And if you want, for task periods, they say that by increasing periods, if something is schedulable here, then by increasing period is always schedulable. What does it mean? It means that from here, if you move on any direction, like this way, this way, this way, and so on and so forth, then we have schedulable. Yes, we get schedulable tasks. Okay. Okay. Fine. Is it clear? Right. So optimal execution time. So when I say optimal execution times, I mean that I assume the variables to be the execution times of tasks. Okay. So basically, X is the set of all computation times, and so I consider the case where the task set is entirely given, except for computation times. So we know periods and deadlines, but the computation times are our design variables. Okay. Right. So in this type of problem, basically yes, we have the execution time which has to be found such that this performance as a function per computation time is maximized. Okay, let me see. Yeah, for example, I think we showed maybe last class or maybe the first class that in fixed priority, the feasible region of computation time is we know it, C1 and C2. So it was something like maybe, well, it's too bad. I think I drew something like this in one of the previous classes, and this was the feasible region. Basically, solving the design problem onto the computation times means that we have to solve the optimization problem over this region. Okay? So here we have a cost function. Let's say we have a cost function which has these level curves. If you want, here they have the maximum. Maybe, yes, a separable oil or whatever. Okay, so we have to maximize, so we have to go in that direction. Then let's say the optimum then is this point, or whatever it is. Okay, this is the interpretation of this. Right. So typically, well, one notable case is when you have the performance function that are dependent on the task only. So basically, you have a performance function per task. So in this case, then you have just a function ji, so it's a task-dependent performance function, which is a function of the computation time, right? And then since you have n of these guys, so n of these guys, then you may want to find a way to combine these n guys. And a way that you may do, well, one is you make sort of linear combination. That is something that the people sometimes does. Let's say you make a combination, a linear combination of the performance of each task. Or another way is this one, when you call, let's say, big J, the overall performance equal to this. Or another way could be that we set the overall performance equal to the worst performance among the tasks. Okay, this is a sort of more balanced way. So basically, you want to maximize the lower performance. So you have a set of tasks. So you just want that the worst among them is as good as possible. Okay. Okay. Right. So if we assume this performance function, and we assume that, which is something quite natural to do, that the performance is non-decreasing with the computation time. This is something that you always expect. You expect that a task, the more it executes, the better performance it delivers. So that's quite, I mean, I don't see any reason of running a task longer if it decreases the performance. So it doesn't make so much of a sense. So a very classic, very natural hypothesis this one is that the derivative of the task performance with respect to the computation time is non-negative, so it's positive or zero if you want. And so if you have this hypothesis, then basically the solution of this problem, we can say already something just from this very very weak hypothesis. What we can say from the solution is that we have this property holds that at the solution, all the cost will be the same. And why this? So let me explain you in this way. I'll make the case of computation times, right? So we have C1 and C2. So let's say we have something like this. This is the feasible region, and then we have the cost is increasing per task. So basically, the cost of this is J2. J2 increased as function of C2 only, increased this way, and J1 increased in this way. Okay, this J1 is function of C1 only. Since the combination of the overall cost is the minimum, then the combination of the overall cost is the minimum. Let me see. So let's say that at these points, the two costs are equal to each other. Let me just think a second. So on this side, the cost of J2 is increasing, but the cost of J1 is constant. So since you are taking the minimum, yes, the level curves are like this. So the level curves of the mean of J, so these are the level curves the level curves of mean of J, mean J1, J2, J3, and J. Okay, they are like this. And so, well, this point is the point corresponding to the case where all costs are equal to each other. So, because of the sustainability, if you want, of the schedulability region, and because of this shape of the cost, the optimum in this case will always be in this condition. So the optimum will always be along this path of having all costs equal to each other, and it will hit, since the cost is increasing this way along this path, it will hit the boundary here. So basically, the solution for a problem where the overall cost is written this way and the schedulability region is sustainable is always at a point in which the costs are all equal to each other, and these are, if you want, a constraint, n-1 constraints, because they are n-1 equality, okay. And then the boundary is hit, and the boundary is, if you want, is one other constraint, okay. So you find a solution by intersecting this n-1 constraint together with this condition, okay. This is a sort of optimization. Any question? Is it kind of clear? Or?
But this makes sure that the costs are similar, right?
Yes. I mean, if you choose, I mean, the costs are similar.
Okay.
Is implied by this because you want to maximize the minimum cost, the minimum performance. I mean, we are talking about performance. J here is a performance. It's something that you want to be big. Okay. So if I say, sometimes I may say cost because if I do say cost, it's my mistake. It's performance. I hope that all my slides are consistent with this. Okay. So I want this to be big. So I mean, choosing to maximize the minimum amount of the task means that we want to push up the minimum, meaning that we want to push up all of them, right?
Means that the all execution time should be almost equal.
No. All the costs corresponding to all computation time must be almost equal.
And which is a physical interpretation of the cost?
Physical interpretation of the cost is the accuracy of an MPEG player. I don't know. And then
the timing analysis.
No. The cost is the cost. Okay. Thanks for this. The cost is the cost in the application domain. No, performance again. Let's talk about the performance. Is the performance that a task can deliver with that computational time. Let's say that you have a model predictive control. Okay. Model predictive control has many numerical routines. Routines that are based on iterating something. Okay, until you find something else. Okay. So the more you iterate, the more accurate answer you get.
Something like imprecise computation.
Exactly. So the more accurate, the more times you run, the more accurate is the result that you get. So if you want, performance is related to the accuracy of the result that the task delivers. Okay, and it is function of the computation type in the sense that, I mean, let's say I didn't draw that, but yeah, let me take a note that this may be something good. With an example of costs. Of performance. Okay. So, for example, let's say that your performance has to do with the numerical routine. Typically, well, if you do not execute, you have low accuracy. When you start executing, where you execute for some time, you have some accuracy, but maybe you saturate. At some point, I mean, it doesn't matter because of numerical precision of the machine. Maybe you don't gain anything by executing, I mean, too much, okay? And you have to think that each task does something different on its own. And then maybe every task may have a different function doing it. Okay? Is it more clear? Hopefully. Okay, yes, this is always something that one can do. Of course, if finding the exact solution is complicated, I mean, one can always compute to solve the problem over some sufficient test, and which makes the solution very simple. So if you use, for example, a linear the upper bound on the utilization, this is just a linear constraint on the computation time, and that makes the problem very easy. So for example, if you have C1 and C2, the linear utilization bar is something like this. From this constraint and this constraint, let's say we have this cost, this cost, this cost, okay, we find that this point here, right? So something like this, very simple and easy. Okay. Now let's talk about periods. Well, with the periods, the question is if you want the same. Now we assume that our design variables are the task periods. I consider this, well, I don't know, it's hard to say what problem is more relevant or not to the reality, but this is certainly a problem which makes a lot of sense in control system. In control system, you have tasks which just compute, for example, a control law. And actually, in those cases, in control systems, estimating the execution time is quite easy if you want, because it's just a matrix multiplication. It's reading sensor, make a matrix multiplication, then apply actuation to the actuators. Okay? But the variable in that case is to choose the sampling period. The sampling period, which are, how often do I sample, how often do I run the controller. Of course, each controller in isolation would like to run as fast as possible. That's obvious. But then when you have many controllers, you have to combine the needs of all of them. Okay, so right. Yes, choosing simple period of controllers. Yes, sometimes I think I'll use this actually quite soon. Okay, of course, the variables in this case are periods, or equivalently, I will use the frequency of activation. So I just denote Fi, just 1 over Ti. This is just something that is convenient sometimes. Well, I mean, I can tell you immediately the reason why it is convenient, because if you write, let's say, utilization upper bound in terms of frequency, then it becomes linear, right? So that's something that makes it convenient. Because if you write it with the periods, then it's not linear. But if you write it with the frequency, it's linear, so it's not. Okay? So I can leave it here. Right, so execution times in this case are specified, what the design parameters are instead of the periods, or equivalently the frequencies. And deadlines are typically either absolute value di, or they are just expressed as a ratio of as normalized to the periods. And the problem is just the same as before, where the variables instead are periods, and we want that it is FP schedule. So everything is the same. Now the question is, what is the geometry of FP schedule periods? Because if you remember, when we did sensitivity, with the sensitivity analysis, the geometry of computation time was found because we had those linear inequalities which had to be combined with AND or OR, and we were producing that type of shape, if you want. Okay, the 3D, maybe you remember. With the periods, however, we did just an algorithm to compute sensitivity. We did not visualize anything. We were not able to find analytically a visualization of the space of feasible speed. So it's something it's worth investigating. Okay, now I want to do something, but I want to let's reason a bit about what could it be. Okay. Now I will work in the frequency domain, right? So I want to find what is the domain of exactly feasible frequencies. I'm assuming that to have a computation time of, well, in this case, right? So computation time of let me see, okay, I want to just draw, okay? So computation time C1, 1, and C2 equal to 2, okay? So what I know for sure, let's first make some clear statements, okay? First of all, it has to be contained into the EDF schedulability condition. Okay? The EDF schedulability condition is this one. But we have two variables, I can avoid use the summation. So C1 F1 plus C2 F2 less or equal to 1. With those values, C1 equal to 1 and C2 equal to 2, this region is like this, okay? So no matter what, it has to be inside here, okay? Because this is EDF. Okay. Then it has to be, of course, I mean, here we have Buell Leyland. So it must be a subset of EDF, but it must be a superset of Buell Leyland. This is obvious, right? Okay, now let's reason about some facts, some information that we have. One information that we know is that if task periods are harmonic task periods, I mean, for those of you who don't know, in two cases, just means that T2 over T1 belongs to natural numbers, okay, with two periods, with two tasks is this. Now, if you are, which is basically the same as F1 over F2 belonging to the natural numbers. So if F1 over F2 belongs to natural numbers, then we know that EDF is exact. Okay, we know it because I mean, this is well studied and so on and so forth. So what does it mean in our plot? Well, it means that when this ratio is integer, then we know that. Okay, when is that ratio? Well, this ratio, for example, is 1. Well, that ratio is 1 over here. Right, over here, that ratio is 1. Here we have the frequencies that are the same. So the same means that the ratio is 1. Okay, so let's say when is that ratio 2? The ratio 2 is, well, let's write it. So we have F1, F2 equals to 2. So, yeah, that's right. So, yeah, over here, when on a slope 1/2, on a slope 1/2, so this is a slope 1. This is slope 1/2. This is slope 1/3. Okay. Okay. So along this, we have integer. Okay. So basically, since in these cases we know that EDF is a fixed priority schedule, then these points and so on for 1/4. These points belong to the exact fixed priority schedule region. Okay. Now we call another notion. We invoke the notion of sustainability with respect to periods. Sustainability with respect to period, what does it mean? It means that if by increasing periods, we always keep schedulability. In task frequency, it means by reducing any task frequency, we keep always schedulability. So from these points, we know that by reducing any task frequency, here, 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 okay, we always have schedulability. Okay, this is just a simple, I mean, basic reasoning. It's not super advanced math. Okay. So we know these points. Okay. And we know that by reducing any such frequency, we have causal. Okay. So we have reduced pretty much the amount of uncertainty. I mean, over here, we don't know. We don't know yet. It's something that we will investigate. Okay. But already it's a good result. Okay. And probably you can understand here the points becomes very dense because here, and then in the end we are going to include all points. Okay. Right. So basically we have this situation, which is somehow the same as which I drew. Okay. Right. So well, that's also another interesting observation. Yeah, if we have this property of increasing performance per frequency. So if the performance is always increasing with respect to any task frequency, then all vertices are local optima. This is kind of geometrical, natural way to because this property implies that the gradient of the performance is always into this cone, right? Because both components have to be positive. So the gradient has to be always onto this cone. And if the gradient has always to be in this cone, well, all those points are always local optima. No doubt about that. Okay? Questions? Okay, now we know somehow the region. Yes, that region is the exact region. I mean the amount. So I will show you later also. But yes, this region is the exact one. So here are all non-schedulable. Okay, but I will show you this later because now I need this. So what could we do to solve solve the problem? Well, one method could be this. Look, we have this strange shape, right? We first solve over the EDF constraint. Let's say that we maximize this performance, which has, let's see, a point here or something, or maybe I like it more like here. Okay. Then what do we do? Using the sensitivity analysis to find the scaling, okay, the minimum scale, the scaling that we need. Well, let's see. We solve the problem on EDF. On EDF, the constraint on EDF is linear, so I mean we can solve it very easily. So we can find easily this point. Now using the minimum speed, the sensitivity of the minimum speed, which is something I showed you last class. Minimum speed is the minimum scaling, and the scaling in computation time is the same as the inverse of the scaling of, well, if you want, it's the same of scaling of frequency. So with the minimum scaling, we find a point where we hit here, okay? Now then, since we have this property, by increasing any frequency, we can we can just do anything. We can just increase the performance. So by using the period sensitivity, that is that strange method that I explained in the last class, from this point we can search for what is the amount of, period decrease or frequency increase, which is tolerable, keeping visibility. Which means that we may go here. Okay? Okay, so now what is the problem? The problem is that this method does not guarantee optimality, of course, it's just a heuristic. Because if you have like, well, the optimal could be something, it's just a heuristic, it's not guaranteed. Optimality is not guaranteed. Right, so, let me drink a little bit of bread. No. So what would it be instead an optimal search? An optimal search, well, the optimal algorithm to find the solution could be as follows. But first, we start from a very good solution of fixed priority, which is the one that I described here, because this is already, I mean, a pretty good approximation. Then, by using branch and bound, in a way that I will not explain here, but if you want, I can provide you references to papers. Let's say that by this solution, by this method, we find the solution. Then we know the cost here, and we know that the cost here may be something, let's say we draw the level curve of the cost here. The level curve of the cost. So basically, any point which can improve the performance here must necessarily be on this side of this curve, right? Because deposits are below are necessarily lower performance. So the only space, or the only room for improvement of the solution are the points, in this case just this one, where you have a higher performance but still schedulable. Okay. Basically, the idea is to search for the vertices which have higher performance, but which are, you know, on this bound, these corner points. Okay. However, enumerating the vertices is something that, I mean, maybe in 2 dimensions you can somehow understand, or you can somehow try, but in 3, 4, and dimensions it's not so clear how to do it, right? Or it is clear. Is it clear? What happened?
Do you do it in 2, 3, 4, 5 dimensions?
Myself?
Yeah.
Yeah, I mean, we have a routine to do it in a dimension. I mean, but it takes, of course, the higher the dimension, the more problem, the more difficult is the problem. So how do we enumerate vertices in n dimension in a general case? Okay, to do it, I need to write once again a new way to write exact fixed priority schedulability condition. It is somehow hard to read, but I mean, the rationale, if once you understand the rationale, the math comes for free. So basically, if you remember, let's first remind you the original schedulability condition, which you may remember. Well, now we have, yes, we are in the constraint deadline. So basically, in the constraint deadline, we wanted for all tasks from 1 to n, we wanted exist a t in 0 deadline, or if you want, I mean, here, since I'm assuming constraint deadline in 0 period, such that what? Such that the computation time of the task plus the interference is less or equal than this point t. Okay, this is the condition that you should feel confident with. Okay. Then, of course, you know, in the last class we saw how to reduce this set, so on and so forth. But I mean, I'm fine with this. I mean, let's work with this. Now, this condition, the condition I'm stating in the slide, is more complicated, but has somehow the same shape. Why that? Because it has for all tasks, it exists something different. So basically, I'm requiring to exist. I'm requiring that it exists a tuple of integer vectors, k that are denoted by ki. I mean, k is the vectors of the length I minus 1, and yes, and related to the schedulability of task I, such that something happened. Okay. Okay. Let's see. Let me first, well, these two conditions, I mean, the condition is here and here are equivalent. And I want just to give you the sketch of this proof of equivalence, but and then probably you will understand why this math. Okay, let's say equivalence means that we want to show that this implies this. We have to show both implications, right? Of this condition implying this, and the condition on the whiteboard, no, on the the screen, well, if you want, both, implying this down here, right? So let's see. I want just to show you. Well, let's see how much time I have. I want to start from showing you that if this is true, then the one projected is also true. How does it work? Well, if this is true, it means that we know that for all tasks it exists a T such that this happens. Okay, let's define. I say let's define, and I have to prove that for all I it exists also this K. So the only problem here is how to find those Ks. To find those Ks, I define those Ks according to this. If I define those Ks according to this, then what happens? I have to, so now, from the beginning, we know that for all I exists T such that this. I define K like this, and I want to see if this case satisfies these properties. Now, for all I exist K, so let's see if it satisfies this property. So if I plug those K's here, I get exactly, let's see, I get what? Yes, I get exactly this. So the right-hand side is exactly this, which I know from hypothesis being less than T, and I want this to be less than Ti, so it's fine, because since T is in here, it's also less than Ti. So the K that I choose in this way certainly satisfies this condition. Now, let's see. Because of the ceiling properties, then from this choice of K, I certainly know that, what do I know? I know that K, J, I is ceiling, so, well, minus 1, let's see, Tj, less than T, is equal than K, J, I, T, J. Yes, so this is just the definition of ceiling. Definition of ceiling, okay? So, and then if I just, since I know that, I mean, you can recognize the similarities with this, okay? So basically, I want to make the long story short. I don't want to enter into the details of the proof, but the point is that by choosing the K in this way, okay, basically, those K satisfies also this property. The other implication is what? Is that we have K's and we have to find the T. And how do we choose T? We choose T according to this. If we choose T in this way, basically interpreting the K basically as the number of job interfering in T. If we do this choice, then we will find out that the T chosen this way will satisfy this property. Okay? So without, but you know, the details are in papers, and so I mean, these are not really important here. Okay, now, why do I need this kind of crazy way to write physical discriminability? Because in this way, the advantage is that I isolate periods. Now periods do not appear inside the ceiling anymore. I mean, this K was the trick to bring periods out of the ceiling. So now dividing here, bringing there, making some stories, basically I can rewrite equivalently the previous inequality as in this way. So in terms of task frequencies, so Fi as so task set is blah, 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 if for all I exist k such that fi is in here, is in this boundary, and fj and fl, for all this l, is between these boundaries. So you can see that here there is no task frequency, here and here, and here there is no task frequency. Okay? Basically, this is just a box, if you want, because in the space of frequency, it's just a box, because you have each frequency is bounded from left and from right. The other frequency from left and right, so this is just a box. And since we have to do for all I exists k, see, as we did in the computation time case, the exist is a sort of union, and for all is intersection. So this, the shape of fixed priority scalable frequencies, or periods is the same, is going to be the intersection of union of boxes. Okay? So this is one box. By this we do union, and by this we do intersection. Which basically is the same as we had kind of thought, okay? So basically here you have to think this as a box. This is another box, box, many box. You do the union, and you find this, and then you do intersection, meaning that you consider also the schedulability of all tasks. Okay, this is basically somehow a sort of proof that that the kind of the field schedulability region that we guessed is exact, which is exact. Yeah, let's see if it's. Yeah, let's make a 5 minutes break.
Here, n is a finite or what?
But the number of blocks to be united are infinite. It's infinite. And yeah, but as you know, here you have these kind of things, and also.
We have to stop somewhere.
I mean, the exact schedulability region is composed by an infinite number of vertices. Okay. Then, you know, when you are into making a practical usage of it, then of course you have to first stop somewhere. But the exact region, if you view it in the frequency space, is composed by an infinite number of vertices, becoming denser and denser here. And it's like that. So, I mean, you have to live with it. So, if you want, I mean, of course, if you have to do optimization, a quite natural observation would be that, look, at some point when these vertices are so close one to the other, it doesn't make so much of a difference if you pick one or the other one. Right? I mean,
depends on the granularity of the.
Exactly. So I mean, but here maybe it does make a difference. Right? So, but you know, I mean, if we want to be precise, the exact region of feasible frequencies is composed by an infinite number of these boxes.
Can you go to the previous slide?
Yeah.
So K is the occurrence.
K is
occurrence of the.
K is the number of jobs interfering into the response time. K is the number of jobs.
Occurrence. It's kind of occurrence.
It's a kind of occurrence of high priority jobs. Yeah.
And what is NJ?
NJ. Oh. Nothing. It's a mistake. NJ. Thank you, Celine. This was a very good one. Wow. Let me take a note. Wow. NJ is a mistake.
Because
no.
Why you have written N?
No. It's K. It's K. Oh, there's a mistake here. It's supposed to be K.
Okay, please. You can say binary executable. Not binary, it's extra files. Then you can say find the so. No, I'm saying it's useful or not, I don't know. It should be like only one or two.
Hi, Enrico. For me, this method, this solution is perfect. I mean, I cannot see any weakness. I cannot see any weakness or imperfect part for this work. So, what's your opinion? Do you think this is a perfect work, or if there is some imperfect part of this work? Just
yes, right. I mean, this is the exact characterization of activation rate. So I mean, it's not. I mean, there is. I mean, it's proved. So there is no space for improvement in the characterization of task periods. So if you want to think of weak points or places where I mean, I think in the last slide I also list a couple of open problems that I think are all interesting. So maybe I can postpone to later, but I mean on the fly I can answer that. Yes, of course, one weakness is this set. Here we have we are asking to check if it exists a tuple of integers into an infinite set. So it's not a test that you can practically use. So I mean, also the ability to reduce that would be, or maybe as we were discussing a bit with Sunil before, we have this type of shape, right? With infinitely many here points there. So let's say that for some reason we know that we are interested only in some subset of this area. Probably translating this into a reduction of this set is something which may be useful. Somehow it is already in the paper, because in this paper we did optimization, actually the exact optimization. So I think if you want, with playing with the frequency, there is not so much space. Maybe one issue is that the claim that well, it depends if you want to work onto the schedulability condition. Well, let's go back a second to the first slide. Okay, this is the very first slide, right? So this formulation is a work about here. It's a work about the schedulability region of fixed priority tasks. Right? We assume that the performance is a simple function of task periods. However, this is not so the case, because, for example, in control system, I mean, I have a slide here. Well, maybe I can, let's keep that question.
Okay.
Write it down and we discuss it at the end. Because I have a slide of open problems and we see if, that the slide, I mean, you find that slide satisfactory or not, or is there other?
Okay, that's fine.
Okay.
Enrico, one more thing. The previous here the C is the cost, or C?
No, the C is the computation time.
Computation time.
Yeah. Here it's only about the formulation of the schedulability region. Sì, anche prima, no? Entro sì.
No,
Sì, certo, ma anche prima, no? Yeah, C are the computational time. Here it's only about the schedulability region. So for the moment, for this analysis, we forget about the performance function. Then we use it in the optimization methods, but not in the formulation of the schedulability region.
Because previous slides you have used C for the cost.
Where? I hope I never did. No, where? Now you. I think I did use J.
Let's see.
But here is a variable, right? So here I'm saying that the cost, the performance depends on the cost. On no, sorry. The performance depends on the computational time. Okay. Blah 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 blah. Okay. Branch and bound. Yes. Okay. Now we have that formulation. If you want, you can use branch and bound algorithm. We have a paper that is this question mark, okay, and where we find these task frequencies. Of course, it's complicated, and you can always use linear bound by using here just a linear upper bound. And it was done by Seto, and it is suboptimal because, of course, its region is smaller. But the advantage is that you can find an explicit solution. Okay, beyond. Now let's enter a bit into a more general problems. The question now is, well, look, is the performance function function J depending on the periods or frequencies only, or not? Well, in reality, for example, in control system, which is somehow the motivating application domain of this work, it does not. It does not because, well, because the controller is not just sampled and actuated periodically always. It does the way you actuate to a place does depend on the schedule itself. So it's not really sampling and actuating periodically and then changing the period just is a way to change the instance when you sample and you actuate.
You mean to say that the actuation overhead is zero for an end user?
Yes. I mean, in the controller, when the people computes the function J of t, Ji of ti, to compute this function, it is assumed this type of schedule, periodic and completion, periodic and completion. Okay, because it is assumed that actuation at release and sensing at release and actuation at completion occurs at the same time and strictly periodically. This is not the case because the reality instead is that you have many tasks. Well, let's say you have activation here and completion here, so you have sensing and actuation here. This task instead has maybe even like a preemption, so even the pattern is different. So the reality is different from the assumption that are behind the computation of this function. Okay. So right, the reality then a task scheduled over CPU over a shared execution platform has a delay jitter, yes, which depend of course on the task parameters. Here I just make an example. If, for example, let's say we have two tasks with computation time C1 and 2.5. I just made an example. Let's say that you have two periods. One is T1 equal to 1.99 and T2 equal to 5.0253, whatever, okay? Then let's say these are two periods that you have. And right, so if you have these two periods, the response time of the task 2 follows this pattern. I mean, if you do the math, you will find out, okay? For this very strange pattern, well, strange, very noisy 5.5, 5.35, 5.45, 92. So it's really a crazy pattern with a maximum response time at 0.6.0. So I did it. So I mean, very weird and long, which occurs at job 40. So the response time of the second task is very long. However, if you make just a small perturbation of the periods, let's say 2 and 5, it was 1.99 and 5.0. So very, very, very small perturbation of the task periods, okay? Basically, the pattern that you get of response time is very simple. 5.5, 5, 5.5, 5, okay? Which repeats every 2, so it's very extremely simple. So this example is just to say that the jitter that is how much the response time pattern varies over time, is discontinuous over the task period. Because by making a very small perturbation of task periods, we achieved a very big jitter variation. Because here the jitter, let's say, is 0.5. Here the jitter is maybe it's close to 0.5, but the pattern that you get is from 5.5. Yeah, but the response time jumps because I mean the worst case response time here is 6 and here is 5.5. So you have a big variation of the response time pattern, okay, with a small variation of periods. So basically, an optimization method which is jitter aware is not simple. You cannot use classical continuous methods, smooth, mixed Lagrange multiplier and stuff like that. Because, I mean, these techniques assume a sort of continuity of the cost, continuity of everything. But here, if you make a small perturbation of periods, then you have the response time that jumps, which has a big impact on the cost, on the performance. So, I mean, this is something that one has to consider. So maybe the techniques to solve, I mean, this problem in reality has to be different than the techniques used with continuous variables. So, well, ideally, if one wants to solve this problem, one would need to identify how the task periods do affect and priorities, if you want, the schedule, then to see how the entire schedule affects the performance, and then then solve the optimization. And this is somehow relative recent research area, because I think it's quite difficult. Problems are quite difficult, so it's not something that is one solves like direct. So there are some results, and which I will include in the course note, I hope, if I remember. And yeah, but there is still space for some contribution. And if you want, yes, I'll select here a couple of open problems or problems maybe are interesting. And well, for example, how do the task parameters affect the task schedule? For example, the pattern of job start time. So the job, we know that, right, in fixed priority, you have this high priority task. Okay, and then we have this lower priority task. And then this. If sensing occurs at the beginning of the job start time, it's also interesting to know what are the start times as a function of the task periods, and in a way that you can, but not just the longest start time. So the entire pattern of start times as a function of the task periods. Or maybe also the pattern of job response time, the entire pattern of job response time. Or if you want the distribution, if you see the response time as a sort of random variables, what's the distribution as a function of the task parameters? Or if you want the joint distribution of k consecutive response time. Let's say if now the response time is something, for example, in the example I saw before, the response time here is somehow very deterministic, because if you know that if now you read 5.5, next you're going to read 5. So it's really deterministic. Here is a bit more kind of chaotic, something that we don't know. And then from the performance function perspective, but this is something that has more to do with the application domain, something which has to do more with the control, if you want. Can the controller design be improved by the exact knowledge of the pattern? Because as I told you before, I mean, the control people tend to work with this kind of instantaneous model of sampling and actuation. Can improve the design of the controller by knowing the exact pattern. And how robust are the controller to variation in the task schedule? I mean, if we have this problem that a small task parameters variation change the response time pattern by a lot, how sensitive, how robust is the design of the controller with respect to this variation? These are all, maybe these problems requires a bigger knowledge of control system, or actually some more knowledge on the application domain. If your application, I mean, the same problem can be stated on a different application domain, in the domain of an NetPack decoder, in the pay because this has to do with the application, right? Well, this has to do with the scheduling. If you want, this has to do with the performance function. Okay, if you want, this second problem has to do with this part of the problem, and the first problem has to do with this bottom part. So these are like related to the performance function, and the problem here related to the skill of the individual. Okay, yes.
Excuse me. Here the exact knowledge of sampling and activation times. This means the worst case scenario does not hold here, because we know the exact activation.
Part, yes.
Okay.
One would like to know the exact part. The worst case is just one length, right? It's the longest.
Yes.
In the worst case scenario, the worst case is the longest response time or the latest start time, things like that.
Okay.
But I mean, how maybe designing a controller based on the worst is not good.
Pessimistic.
It's pessimistic or it's wrong or something. So maybe knowing the exact pattern can improve the design.
Is it something related to the synchronous reactive program?
Synchronous reactive. I don't know. Synchronous reactive. What's that?
I know it was a task problem proposed by Sanjay, and he's working on this.
Synchronous.
So basically, if you have, as far as I understand, in this model-based development, you assume that some activities are instantaneous, which does not incur execution time. So whereas in the actual system, they happen serially. So how do you schedule these kind of things? So when you actually implement this actual model in the system, how do you schedule them so that the assumption of that it happens instantaneously is actually valid in the implementation also. Something like that. I mean, I don't know.
Maybe.
Maybe.
Any other question? Comment? Okay, so we can stop and stop the recording. Interrompi trasmissione.
Yes.